Okay, so what we want to do today is a short review problem, and it's going to be made up of several sections, and they're all going to be related one to the other, and it's kind of going to cover all the material. And the only misleading statement was that it's going to be short. It's not going to be that short. Okay, so here's the problem. We are given three surfaces, and I'm already regretting what I'm doing. I'm going to rewrite this because I want to keep a lot of data on the board, so I'm going to rewrite it smaller. So we are given three surfaces. The surface A is the set of points that satisfy x squared over 9 plus y squared over 25 equals 1. So this is the surface A, or if you want to write it more formally, A is all the points x, y, z such that this is satisfied. So that's the surface A. The surface B is all the points x, y, z in R3, satisfying that z equals 4 over 3x plus 4. And the surface C are all the points x, y, z, satisfying that z equals 0. I don't know why I put these lines. They're not necessary. So these are the three surfaces. And in addition, we have two given fields. So the fields are going to be called F. So F is the field y in the I direction minus x in the j direction, and x times z minus 4 in the k direction. That's the field F. And the second field, G, is 0 in the I direction, 4 minus z in the j direction, and minus 2 in the k direction. So this is the data. Three surfaces, two fields. And V, so let's write it here, let V be the solid, or the body, bounded by B from above, C from below, and A from the sides, on the sides. Okay, and now there are 8 questions that you have to answer. I'm not going to write all 8 and then answer them. I'm going to write one, answer it, write one, answer it, so we can keep track of what's going on. So here's part 1. Let's call it little a. A. So what is the shape of A, B, C, and V? So that's part A. Understand, decipher these geometric objects that appear in the problem. So let's get started. What is the shape of A? So let's look back at A here. So A is the set of points in three-dimensional space that satisfy this. So what is this equation? What does it represent? Right. In 2 dimensions, it's an ellipse. An ellipse is not the right answer, but what you said, cylinder, that's the right answer. So for Z, there's no restriction on Z. So for every z, we're looking at all the points x, y, z, that the x and the y satisfy this, right? So for every z, we have an ellipse. This is obviously an ellipse. And that ellipse is sitting in every z. So it's an elliptic, cylindrical, that's A. Do you agree? So let's write that. A is an elliptic cylinder. Good? What is the shape of B? So again, remember that these are shapes in three-dimensional space. Okay, so you can say, hey, this is an equation of a line in the xz plane, which is true, but that's not what we're looking at. We're looking at points x, y, z satisfying this. So there's no restriction on y. And what is this thing? Right, it's a plane. Right, so in for every y, we have this line in the x and z coordinates, and this line is smeared for every y, and we just have a plane. You can, of course, rewrite it as a standard equation of a plane. Right? So let's do C at the same time. What is C? Right, it's the xy plane. Do you agree? Okay, so B is a plane, some tilted plane in the xz coordinates, and C is also a plane, but it's not just any plane, it's the xy plane. Does everybody agree? Questions? Okay, what is V? So remember that V is the solid, or the domain, bounded by B from above, C from below, and A on the sides. So A is this cylinder, C was the xy plane, and B is some tilted plane, right? So V is some part of this cylinder that's been cut off on the bottom by the xy plane and on the top by this plane. Do you agree? So we can even draw it. So V looks something like, I'm going to draw here something and then erase it. So it looks something like this. Here's this cylinder. On the bottom, it's cut at the xy plane, and on the top, it's cut at some tilted plane like this. Do you agree that this should be something like the shape of V? Everybody? Okay. And as a matter of fact, I have solved this problem on the board several times thinking that V looks like this. And only after a couple of times I realized that it's not accurate. And I'll tell you why. Maybe you can see it already. It requires some thinking. But the point is that it's not crucial. Okay, so sometimes being able to draw the shapes you're working on is not an essential part of solving the problem. It helps. It's a good thing to do, but you shouldn't feel, this is kind of a tip, you shouldn't feel that if you can't draw it, that's it. You're lost. You can't do anything. Okay, and this is an example where, okay, so why doesn't it look exactly like this? What's the difference? Anybody have a clue? Well, I didn't tell you where the axes go, so you can say, okay, maybe it's turned around, maybe it's tilted this way, okay, which is correct because this plane is diagonal on the xz plane, right? But there's a more tricky little thing to observe. So let me tell you, this point here, and this point here actually coincide. That's the thing to notice. So in fact, this tilted plane B, it's tilted. It's going to intersect the xy plane, obviously. But in fact, it intersects it precisely at this point. And therefore, the correct shape of this thing is not this, but rather something like this. Here in the back, we have this. That's the correct shape. And this point here, where they intersect, so we can figure it out. The z is going to be 0, right, because it's the xy plane. When z is 0, x is going to be, what, minus 3. Do you agree? When z is 0, on this plane here, x is going to be minus 3 in order for z to be 0. Does everybody agree? And when z is 0, and that's fine, when x is minus 3, you get that, what? 1 equals 1, so y is 0. Do you see that? So the point minus 3, 0, 0 satisfies all three surfaces, and therefore that's that intersection point. Clear? Everybody good? Okay, so this is the shape of V, where the sides are A, the bottom is C, and the top is B. Question so far? Okay, so that was part A. Part B, yeah, let's use a new board. I'm going to solve this rather slowly so everybody can follow and understand everything. But I think you can appreciate by now that if you're already prepared for the exam or for life, then this is easy, right? It's not too tricky. Okay, part B. Find the mass of V if its mass density is given by rho of xyz equals 1. So in fact, it's a constant mass density. So for any form of shape, whether it's two-dimensional, three-dimensional, a curve, a surface, when you're given the mass density and you want to know the mass, you integrate over the mass density, right? We discussed that several times. So in this case, V is a three-dimensional object, solid. So we just have to do the triple integral over V of this function 1. Do you agree? Okay. So the only thing we have to figure out is how to write it in a way that we can solve the triple integral. And for that, we need to express V as a simple domain. So we can write the integral as an iterated integral. Do you agree? Okay. So let's look at V again. Here's V. Is it a simple domain in 3 dimensions? The answer is yes. The bottom part is just this ellipse down here in the xy plane, right? And then for every point xy down here, it ranges between the xy plane and the plane B. Do you agree? Okay. So let's write that. So the mass, let's call it M, equals, so it's going to be, let me write it in 2 steps. The double integral over the bottom, over this ellipse, let's indicate that by drawing an ellipse here. The double integral over the ellipse, and this is going to be dx dy, of the integral dz of the mass density, which in this case is just 1, where z ranges between z equals 0, which is the bottom, and z equals 4/3 of x plus 4. This is the integral we have to calculate. Everybody good? Okay. How do we do this? So we can start by solving the inner integral, right? We always work iterated integrals from the inside out. So the antiderivative of 1 is just z. When we plug in this, minus plug in this, so we just get the double integral over the ellipse of 4/3 x plus 4 minus 0 dx dy. Good? And now, how do we solve this? Okay, so one option is to try and solve it directly. That could work. You could try. Another more routine way would be to do a change of variables, not to circular coordinates, to polar coordinates, but to kind of tweaked polar coordinates to elliptic coordinates. Okay, so it's not going to be r cosine theta and r sine theta, but rather we're going to use the parameters of the ellipse in order to tweak them correctly. Okay, so let's recall what this ellipse was. Where is it? So the ellipse is here. It's x squared over 9 plus y squared over 25. This 9, this innocent-looking 9, is a 3 squared. And this 25 is a 5 squared. So the a and the b for the ellipse are 3 and 5. Do you agree? So the correct elliptic coordinates to use, so here we're doing a change of variables. And we're going to change by x equals 3. 3, was x 3 or y 3? Which one? Yeah, 3. R cosine theta, and y is 5r sine theta. R ranging between 0 and 1, and theta ranging between 0 and 2 pi. You've all seen this in examples, right? Okay, so what are we going to get? Since these are the ranges, we're going to get the integral from 0 to 1 dr of the integral from 0 to 2 pi d theta, right? And then we're going to have the function here, 4/3 x plus 4. X was 3r cosine theta. So I'm going to put that here, 4/3 of 3r cosine theta. So let's write it. Need more space. D theta dr. So 4/3 to 2 pi, yeah. Thanks. Thanks. 4/3, 3r cosine theta plus 4. That's the function we're integrated. The 3's are going to cancel. And am I done? Right, there's a Jacobian because it's a change of variables. The Jacobian for polar coordinates is just r. And what's the Jacobian for elliptic coordinates? Right. ABR, in this case, 3 times 5r, which is 15r. So here, I'm going to move d theta and dr again. So here we have 15r, and this is j, which is a times b times r for these coordinates. If you don't remember, suppose you have a blackout. Hey, there should be a j there. How do I find it? You just calculate it, right? It's dxy to dr theta. It's a 2×2 determinant of the partial derivatives. 1 second of calculation, right? Everybody good? Okay, so this is the integral we have to calculate. Now it's an integral in 2 variables, and it's not a hard one because the bounds are all numbers, right? Okay, so let's see what we get. Let me erase this and continue here. Equals the integral from 0 to 1 dr. And here we have the integral from 0 to 2 pi. And what do we have here? 4r cosine theta times 15r. So it's 60 r squared cosine theta plus 60r d theta dr. Right? Okay. Now there's a little shortcut that we've discussed several times. Since we're integrating d theta between 0 and 2 pi, the antiderivative of cosine is going to be sine. The value of sine at 2 pi and at 0 is the same, so this thing is going to cancel out. Okay, so this thing, once we integrate, is going to contribute a big 0. So I'm just going to cross it out now. Okay, is this clear? When you do this, you have to understand what you're doing. Okay, everybody good? Okay, so we're left with 60r. The integral d theta is just going to contribute 2 pi. So I'm going to throw that 2 pi outside. So I have 2 pi, the integral from 0 to 1 of 60r dr. And then there's an r squared over 2 from the antiderivative. When I plug in 1, it contributes 1/2. Right? So 1/2 times 60 is 30 times 2 pi. I get 60 pi. Questions? Yes?
On the exam, if we have a cos with 0 to 2 pi and cos slash and a 0, do we have to explain that, or can we just do that?
So the question was, on the exam, can we just do this, or do we have to explain? Here's the answer. And that applies to all the questions that starts with the word on the exam. Okay? If it's an open problem where you have to show all your calculations and all your work, you have to show all your calculations and all your work. Okay? And there's no precise answer to what do I have to write or what don't I have to write. Okay? So I would say first solve the problem without extensive detailing and explaining every little why I added 60 plus 5 and got 65. Okay? And then if you're done and if you have some remaining time, read it again. You may find errors which you have time to correct, and you may say, hey, maybe this requires a bit of explanation. Add some explanation. Okay? So there's no precise answer, do we have to do this or do we not have to do this? On an open question in general, you have to show everything. Show all your work, explain all your steps. That's the best answer I can give. Okay? It depends on who's grading and how he decides to. So, for example, if all of this was worth 5 points, okay, and you wrote everything correctly and you did the change of variables and you wrote it as an iterated integral and everything was correct and you got the wrong answer and you didn't explain this, obviously you're not, a point out of 5 is not going to be taken off for that, right? If it was worth 30 points, then maybe it could. So that's the best answer I can give. I hope it's satisfactory. But that's going to be the same answer for all the questions that start with, on the exam, do we have to write? Okay? What is crucial to write always is when you're using a theorem, you have to verify that the conditions of the theorem hold. That's a must in mathematics. Okay? You can't just throw in Stokes' theorem and just use the formula. Okay? That's always in mathematics. You're using Stokes, you're using Gauss, you're using Green, you're using change of variables, you have to calculate the Jacobian, you're using, here you would maybe want to say that the Jacobian is non-zero, or that it's 0 only at a single point, which we said was okay. So those are the things that usually do matter and are more important to pay attention to. The implicit function theorem has several conditions, you have to verify them. Okay? Okay, so this is part B. Everybody good? Part C. C. Find the length of the curve which is the intersection of A and B. So remember, A is the cylinder, the elliptic cylinder. B is that tilted plane, and their intersection is this ellipse-like curve sitting diagonally up here. Do you agree? Okay. So what we're looking for is the length of this curve here. To indicate that it's a curve, let's add a little direction arrow, which I just chose randomly. Okay? Is it clear that this is the curve we're looking at? Everybody? Okay, let's give it a name. How about gamma? Okay. How do we find the length of a curve? Right. We need to parameterize it first. Call the parametrization R. Then we need to find R prime, find the length of R prime, and integrate that. Okay? So let's do that. So a parametrization of gamma is going to be x equals 3 cosine theta and y equals 5 sine theta, where theta ranges between 0 and 2 pi. Does everybody agree that this parametrizes gamma, the curve? Okay?
Doesn't this parameterize the ellipse on the bottom though?
Yeah, I forgot z. What is z going to be? You're right. So you're right. This parametrizes the bottom ellipse, right? And points x, y, z, where these, the x and the y, live on the bottom, but the z lives on the plane, live exactly on this curve, right? So what is z going to be? 4 over 3x, but what is x? 3 cosine theta. So z is going to be 4 over 3 times 3 cosine theta plus 4. Does everybody agree now that this parametrizes this gamma? Let's write this. And this can cancel out again. Everybody good? Okay. So this is r of theta. Let's rewrite it. R of theta equals 3 cosine theta, 5 sine theta, and 4 cosine theta plus 4. Okay? Now we need r prime. R prime is the tangent vector at any point. So it's going to be what? It's going to be minus 3 sine theta, 5 cosine theta, and minus 4 sine theta for the z component. Good? Okay. Now we need the length of r prime, right? So the length of a vector is the square root of the sum of the squares of the components. So it's the root of 9 sine squared plus 25 cosine squared plus 16 sine squared So 16 sine squared plus 9 sine squared is 25 sine squared, plus 25 cosine squared is 25. And the root of that is precisely 5. Good? So this 8-part problem has been written in a way that everything turns out to be so nice and calculatable. Okay? Questions? Yes?
Can I ask you, like, here you put an R, and here here not, because here was the surface and here is only the boundary. Right?
Ask me that later. Okay, we discussed that many, many times. I don't want to repeat it again now. Okay, so this is parametrization of the curve. This is the length of the, this is the magnitude of r prime. How do we calculate the length? We just have the integral of this, right? Remember? So am I going to fit it here? I think I am. So L, let's write it like this. L, the length of gamma, is just the integral ranging over the parameter from 0 to 2 pi of the length of r prime, which is 5, d parameter, d theta. Good? And what do we get? 10 pi. Good? Questions? Everybody good? Okay. So that's part C. Okay. Part D. Now the big challenge in this question is not to erase stuff that I'm going to use later. Otherwise I have to write it again. So let's see if we can meet that challenge. So part D is going to be find the area of B, which is bounded by A. So it's not the area of B, it's the area, it's the area of the part of B which is bounded by A. So remember, B is that plane. The area of B is, of course, infinite. It's a plane. But we only want the area of B which is bounded by A. A is that cylinder, and it chops off that tilted elliptic cap. And what we want now is, again, this thing, but not the length of the curve, but rather the area of this surface. Right? Clear? Everybody? Okay. So find the area of B, which is bounded by A. So this is the area we're looking for. How do we find an area of a surface? Integrate is good. Okay, so first what do we need to do? Right, parameterize the surface. Okay, find the normal, and then integrate the normal over the domain of the parameters. Okay, so let's do that. So parametry, let's call the surface, how about S? So parametrization. So we're going to have, again, it's going to be based on these elliptic coordinates. So x, again, there are going to be an x, a y, and a z. Let's not forget the z this time. X, y, and z. X is going to be 3 rho cosine theta. Y is going to be 5 rho sine theta. Right? Now I want the inside, so I'm allowing rho to range between 0 and 1, and that covers all the inside. Right? And then z is going to be, again, sitting on this plane. So it's going to be, what was it? 4/3 x, 3 rho cosine theta, plus 4. And again, the 3's cancel out. Okay, so let's rewrite it as r of rho and theta. And it's going to be 3 rho cosine theta. It's completely unnecessary to write it like this and then rewrite it like this. I have no idea why I'm doing it, but I am. Too late. 5 rho sine theta and then 4 rho cosine theta plus 4. So this is the parametrization of the surface S, where theta ranges between 2 pi and 0, and rho ranges between 0 and 1. Good? Everybody? Okay. And now what we need is the normal vector. The normal. How do we find the normal? Right, the cross product of the partials. So it's R rho cross R theta. Right? So here we're going to have a little determinant to calculate. So it's going to be I, J, well, need more space. I, J, and K. And then the components of the partial derivatives. So R rho, so 3 cosine theta, 5 sine theta. I'm going to need to be even a bit more generous. And 4 cosine theta. That's the derivatives of r with respect to rho. And then r theta. R theta is minus 3 rho sine theta, 5 rho cosine theta, and minus 4 rho sine theta. Does everybody agree? Okay, let's calculate that and see what we get. So for the I component, we get minus 20 rho sine squared minus 20 rho cosine squared. So we just get minus 20 rho. That's the I component. Do you agree? For the J component, we get minus 12 rho sine cosine. I like that. Rho sine cosine. Minus 12 rho sine cosine, minus minus plus 12 rho sine cosine. We get 0. And in fact, it's a minus 0 because of the J, but it's still 0. Do you agree? For the K component, 15 rho cosine squared, minus minus plus 15 rho sine squared. So we get 15 rho. Does everybody agree? Okay, so we have the normal. Now we need to calculate the length of the normal. So let's do that. So, what do we want to erase? Okay, let's erase this. Okay, so we want to calculate the length of the normal. So the length of the normal is the root of the sums of the squares of the components. So it's minus 20 rho squared plus 0 squared plus 15 rho squared. So this is 400 rho squared plus 225 rho squared, which is 625 rho squared. And the root of that is 25 rho. Good? Hmm? Yes. Yes, you can think about it if you want, but yes, you need to be able to figure out without a calculator that the root of 625 is 25. If it were 623, then you wouldn't have to know beyond the first 5 digits after the decimal point. Okay? Without a calculator. Okay. That was a joke. Okay. Does everybody agree to this? Good? Okay. So what were we doing? We were looking for the area of that surface. The area of the surface, the area of S, is now the integral, the double integral in this case, over the parametrization. So from 0 to 1 d rho, from 0 to 2 pi d theta. And now inside we have to write the length of the normal, which in this case is very easy. So it's just 25 rho. So the integral d theta contributes 2 pi. The integral d rho is going to contribute a 25 rho squared over 2. When we plug in 1, we're going to get 1/2. When we plug in 0, we're going to get 0. So we're going to have 50 pi times 1/2. So we're going to have 25 pi. Okay? If that was too quick, break it up into the intermediate steps. Do first the integral d theta, throw out a 2 pi, and then integrate the d rho integral. Okay? Questions? Everybody good? Okay. Let me remark, since this is a review, let me remark that we're kind of, from the beginning, we're kind of flowing along elliptic coordinates sort of point of view, whether we're parametrizing the curve or the surface, and we're going to use it later on. But that's not necessary. You can do it in other ways. So for example, in this specific section, in part D, you can parameterize S just by x and y, right? You can say it's all the points x, y in the ellipse on the bottom, where the z is 4/3 x plus 4. Do you agree? So that would be a different parametrization of the same surface. Do you agree? Let's do it. Let's solve it another way and see that we get the same thing. It's good practice. So, alternative parametrization. So an alternative parametrization would be r of x and y this time. And the x is going to be x, the y is going to be y. That's usually what we do when we think of it as the graph of a function. And then the z would just be 4/3 x plus 4. Right? Those are all the points where x and y belong to that ellipse on the bottom. Do you agree? Okay, where x, y satisfy belong to D. Well, not to D, to... Yeah, let's call it D, where D is the ellipse on the bottom. The points x, y satisfying x squared over 9 plus y squared over 25 equals 1. Do you agree that this is an alternative parametrization of that tilted surface, of this? Everybody? Good? Okay. So let's see if we can figure out all the details now. So let's do it. Let's make a somewhat shorter calculation. Let's right away write the area. So the area of the same surface is going to be the double integral over the domain of the parameters. Right? That's what we did here. We just wrote it as an iterated integral. So the area is the double integral over the domain of the parameters, which is that d over there, the ellipse on the xy plane, dx dy. And what do we need to integrate? We need to integrate the length of the normal in this new parametrization. Right? What is the normal for a parametrization which is the graph of a function? Do you remember? So let me write it here. It's going to be the root of let's call this temporarily, this is f x y, this 4/3 x plus 4, and it's going to be 1 plus f sub x squared plus f sub y squared. Remember this? We did it several times. Everybody? Okay. So let's calculate it. So it's the double integral over this domain D, the domain of the parameters, of 1 plus f sub x is just 4/3, right? So it's going to be 1 plus 4/3 squared plus f sub y is 0, right? Plus 0 squared root dx dy. Good? So here you can see that we're going to get just the number. X's and y's somehow disappeared, since it was a very easy function. So what do we have here? We have 4 squared is 16 over 9. 16 over 9 plus 1. 1 is 9 over 9. So we get 25 over 9 in here. We have to take the root of that. That's 5 over 3. Do you agree? So it's 5 over 3. So it's 5 over 3. That was that root over there. That just came out of the integral, and now I have a double integral of 1 over the domain. What is the double integral of 1 over the domain? It's the area of the domain. The domain is that ellipse lying down here, this ellipse. How do we find the area of the ellipse? AB pi, right? A is 3, B is 5, pi is pi. So we have 5 over 3 times 3 times 5 times pi, where this is just the area of D. And after canceling out the 3's, we get 25 pi, just like in the previous solution. Everybody good? Okay. And this is not necessarily harder or easier than the previous calculation. Both are just fine, and you can do whatever is easier or more convenient. Or, in fact, if you're not pressed for time in a problem like this, I would do both and check that I'm getting the right answer. Okay. Questions on this? Okay. So that was part D. There are still parts E, F, G, and H coming, but let's stop this clip here so it won't be too long, and we'll continue it in the same problem in the next clip.